our STEM speaker series. It is Mr. Joe Doughney. He is an engineer with CDM. Before we begin, I would like to take a moment and thank our corporate sponsor, LHC Structural Engineers. LHC is a local engineering firm in Raleigh with more than 40 years experience designing a diverse number of building structures to include hospitals, churches, corporate buildings, and college and university projects. A few of their more notable projects include the Medical School for East Carolina University, the North Carolina Museum of Art, the North Carolina Museum of History, and the North Carolina Aquarium at Roanoke Island, Fort Fisher, and Pine Knoll Shores. We are grateful for their funding and support, which makes this speaker series possible. Please join me in giving our sponsors a big round of applause. So I did a small plug for this audience, but for the rest of our audiences, both at South and online, we have our STEM Day coming up on October the 12th here on North Campus. And without further ado, I will turn it over to Joe.
All right, thank you. Can you all hear me fine? Okay. Hi, as Jackie said, my name is Joe Doughney. First, I'd like to say thank you to Jackie and Wake Tech for having me. They asked me to speak about engineering for a consulting firm, and specifically I'm an electrical engineer. And so I was just going to walk through kind of why I chose engineering, kind of CDM Smith, what we do as a company, and then specifically what I do with electrical engineering. And then at the end, I have I have some photos of some real world equipment that I'll just kind of show you, and then just some tips for new grads, and then we'll have some questions at the end. But I do have a question for all of you first. I'd just like to gauge my audience. Who all is interested in engineering, going into engineering? All right, what about electrical specifically? All right, very good, okay. So, as I said, I'm an electrical engineer. I got my bachelor's from University of Illinois in 2009. That's actually where I met my wife, Erin. It was a 4-year university, and then right out of college, I started working for CDM Smith, actually in Dallas. All right, so I started working for CDM Smith in the Dallas office, and I became a professional engineer in 2014. And actually, I did that in the state of Massachusetts. And so, for the most part, my experience has been with CDM Smith, except for 1 year. We lived in Indianapolis for a little bit, and I worked for more of a mechanical engineering and plumbing firm that did more commercial type stuff. So why engineering? So when I was growing up, I was trying to decide, like everyone in high school, trying to figure out what to do. I always liked figuring out how things worked. And at first, I actually thought I wanted to be an architect, but I took a few architecture classes in high school, and I didn't really like it. So then one of my dad's friends actually suggested engineering, and so that's kind of how, and I was like, oh, that makes sense. I always really liked math and sciences, specifically physics classes. So that's kind of what kind of led me down that path. And specifically, I just kind of threw them up there. If you are interested in going into engineering, you will most likely have to take calculus 1 through 3 and differential equations. And then for physics, I had to take 4 physics classes: mechanics, E&M, thermal, and quantum. So just kind of throwing that out there just to let you know. So within electrical engineering, it's actually a pretty broad topic. So I'm in power. That's what I'm doing. When I say power, I mean, like taking the power from the utility company, running it to this projector, the lights, the outlets. That's what we do. But there's also, with electrical engineering, you have communications, system and controls or instrumentation. You can go into programming or computer systems, robotics, semiconductors, and things like that. So it's pretty broad. So you're probably going to start off with some general intro engineering classes, and then you'll have to kind of choose which route you want to go into. And then for career opportunities, so this is kind of what I list up there is kind of more so what I see in my line of work. So I'm in the consulting world, and I'll get into what that really means. But on the other side of that, so the consulting, we're doing the design work. Then you also have the manufacturers who do kind of design work on their end, who make the equipment that we're specifying and designing around. And then you also have research and development. You also have sales within those. So we have, manufacturer sales reps that come to us all the time, and they usually have an engineering degree. And then you could also go on the construction side of things, or utility company, and then we're designing for clients. So a lot of our clients actually have engineering degrees as well. And then the federal government, you could work for the Army Corps of Engineers. So there's a lot of options out there. So to become a professional engineer, there's a few steps you have to take. And this isn't actually necessary for all engineers. It kind of depends. Like, again, if you're going into research and development, or even in sales, you might not really need to get your professional engineering license. It really depends. I have a friend who's an aerospace engineer, and he works for Northrop Grumman, who is like a defense contractor, and he didn't have to get this at all. But with consulting, all of our designs have to be reviewed by the state, and so they want to see a professional license on all those drawings. So basically, it's kind of like two steps. Well, the first step, I guess, would be you have to get your degree from a 4-year from a ABET accredited college. So the FE exam is the fundamentals of engineering, and then once you pass that, you become an engineer in training, is what it's called, EIT. It's a 6-hour exam. It's given year-round, and it's a computer-based exam. If you can take it while in school, because all you have to do, you can just be anyway. You can take it while you're in school. You don't actually have to have your degree yet, and it's actually good if you take it while you're in school, because all that information's still really fresh in your mind. I took it about 6 months afterwards, and I had to do a lot of studying prior, because you'll be amazed at how fast you start to lose some of those equations and information, especially with all those super high-level math classes. You'll start to lose some of that information if you're not using it on a daily basis. And so the exam is, you do it based on your discipline, but it's still pretty broad. They test a lot of topics: math, science, economics, ethics, and then pretty much all those electrical topics that I listed on the previous page. Those will kind of all be covered, even though you might be steered more towards power or instrumentation or controls. So once you take that, hopefully you pass it, and then you basically have to wait another 4 years. You have to get 4 years of experience, and then you can take the professional of engineering exam. It's actually so this is the exam that will allow you to get. I have my seal. I just threw my seal up, just kind of showing you what's the seal in the lower part of the page is what you would stamp on each drawing. And then you put your signature across it, just so the people who are reviewing it know that it's like, okay, this has been designed by a professional engineer, it's been reviewed by them. So that test is given twice a year, in October and April. And it's an 8-hour exam. It's tested pretty much specifically to your discipline. So with electrical engineering, they have 3 types: power, I think electronics, and then control systems. I think those are the 3. So I did the power exam. It's pretty intense, to say the least. So first off, it's an 8-hour exam, so it's a long time to be at the exam center. And you pretty much want to, since you're going to be 4 years removed from college, you pretty much want to be studying on a daily basis for probably 2 months prior to the exam. It covers a lot of topics in power. There's still a lot of topics, and it also covers a lot of code-related items that have to go into your design. So we have a code book that we kind of have to design around. And you have to pretty much, you don't have to memorize it or anything, but you have to know how to find stuff in it pretty fast. So you have to know where things are.
Excuse me, real quick.
Yeah.
When do you take the PE exam? Is it when you're in graduate school?
No, so this would be, sorry, it would be after you've graduated and you've been working for 4 years in the industry.
Is this a graduate degree, or can you go get a graduate degree on top of this?
You can get a graduate degree on top of this. So this is strictly, you need to be working for, like for instance, CDM Smith, you need to be working for them for 4 years, and then you take the test, you pass it, and then you get your license. They've actually changed it up. You can take the exam earlier now. They just changed this up because when I took it, I could not register for the test until I had 4 years, at least 4 years of experience. Now you can take it sooner, but you still can't get your license until 4 years of experience.
Okay, Heather Hodge wants to know, you took an exam last October that you can sign off on drawings. Is that what you said earlier?
So,
What does that mean? The PE degree allows you to sign off on drawings.
Yes, you sign off on drawings. So you can take it, it's only offered twice a year, October and April. And you have to sign up about 2 months in advance. So if you're interested in this, you have to, and there's a pretty long application process. So you want to make sure you give yourself a lot of time to fill out those applications because you need referrals. People who are professional engineers, they need to give you referrals. You need to get your diploma information from the schools you went to. You need to verify that you actually did pass your FE exam. And then you basically have to, well, at least it's a little bit different from state to state, but I had to show examples of my work from the past 4 years on a pretty detailed level. And you have to submit that every state has their own board. And so it's a little bit, they want to make sure. So FE is basically, they call you an engineer in training. I guess it's basically, really the way I look at it, it's just another requirement you need for the PE, because it doesn't really matter when you take the FE, you could take it the week before you take the PE, as long as you have, you need to get those results, and so, I'm sorry, because you need to know that you have passed before you register for the PE, so you could realistically take them in the same year, if you have those 4 years of experience and you waited that long to take your FE exam. It is, but like I said, it's best to take it as close as possible to when you graduated or if you're still in school, just because it covers a lot of topics that you learned in school, and you most likely, a lot of topics that you may not use again right after school. If it's not directly in line with, because I think I remember there were some chemistry questions on there. I only took one chemistry class in college, so it's more of a kind of to just make sure you had a, kind of a broad knowledge base. And then, once you pass, you technically are a professional engineer. You could stamp drawings. You have to sign your name across it, and then that drawing can go out to construction. Is essentially what that means, and it's, there's no issues with it. It can be constructed. So real quick about CDM Smith. So I said I've been working with them for about 8 years now. It's a consulting, engineering, construction, and operations firm, founded in the 1940s. It's a pretty large company, have about 5,000 people. It's mainly, you can see it's a global company. It's mainly in the US though, with over 100 offices. And what we do mainly is in the water and environmental projects. So when I say water, I mean water treatment plants, wastewater treatment plants, water pump stations. We do some transportation projects and other more commercial type facilities. But I would say 90% of the jobs that I work on are water or wastewater treatment plants. And then with that being said, our clients are usually like municipalities. For example, like the city of Raleigh or Durham or the county, because sometimes the county owns the water rights. So we would be working directly for the city or a county. So real quick, I was just so you can kind of understand where I'm coming from when I say like water treatment plants and just the water in general. So what we have in the top left is your lake or your water reservoir of of your water source. So it's going to come down to a water treatment plant, and that's going to clean your water. It's going to treat it, filter it, disinfect it, and then pump it to, you can see in kind of the upper left, there's an elevated storage tank. And then from there, it's going to go to all of you, to your schools, your houses, companies, and so forth. After that, after you've washed your hands, it's gone down the drains, it's going into the sewers. That water then goes to what they show on the back half is a wastewater plant. So that's, use your imagination, that's all the water that's basically gone down the drain. It again gets filtered, treated. There's many processes, and to clean out the water as much as they can, it's disinfected, and then it's ultimately pumped out to some other sort of water source, like usually a river. So when I say we do projects in water, we are designing these systems, these wastewater treatment plant systems, how it's treating all the water. Same thing with the water plant, how it's treating the water, how it's pumping it to all the residential areas, the elevated storage tanks. There's usually pump stations associated with those. So that's kind of all what we do. We design all those pumps, all those treatment systems. And electrically speaking, it's my job to make sure all those systems have power. And so in the consulting world, I like to use the phrase that my supervisor kind of says, there's 4 players in the industry. There's the consultant, which I'm a part of. Then there's the client, like I was talking about, the city of Raleigh, city of Durham. Then you have, once you've designed a system, it has to be built. So we're not actually really doing the construction. We're doing the design to give to someone else who's going to construct the project. And then there's also the manufacturer. So all these pumps, these motors, the big, at your house you have a electrical panel, all those panels, we have to talk with the manufacturers so we can know exactly what we're putting into the design. And we have to make sure, for like a building, we have to make sure all the equipment's going to fit. So we have to work with the manufacturers to get the dimensions, the cost, and that sort of stuff. So those are I would kind of throw in a fifth, personally for me, a fifth player would be like Duke Energy, because I have to coordinate with Duke Energy about, they own the overhead lines. Well, I have to tell them, hey, we have a new plant right here. I need to bring power to it. So they need to provide me with a transformer so that I can go off from there. Thank you. So those are kind of the main players in my world, the consulting world. With the project stages, so how a project kind of comes to us and how it goes out to construction. So usually it all starts with the client. They have to have a need for something. And so they either need a completely new treatment plant, or most times it's just rehabbing existing facilities. They're getting really old. The systems start to not work as well. So they want to rehab it, or new technology has come out that they want to transfer a system to newer technology. So they kind of approach us and multiple consulting firms and ask us to. They have a request for a proposal. And so then we will, as the consulting firm, we'll put together a proposal. Basically, we kind of give them our resumes and say, like, these are the engineers we have, these are the other projects that they've worked on, and this is what we can do. This is how much we think it's going to cost. And we basically just give them our qualifications, and then sometimes they determine it based on qualifications, sometimes they determine it based on the overall cost, which consulting firm Group A says it's going to come in at 5 million, Group B says it's going to come in at 7 million. They're going to go with Group A, because it's going to be overall cheaper. So once you win the design, or you win the proposal, you start the design. And usually what first happens is a lot of times we have to do site visits. So for me, a lot of stuff is kind of happening behind the scenes. I don't really know all the projects that are proposals that are in the works until we win them. And then our project managers will be like, okay, hey, we won this job. Everyone go out to the site, look at what you need to look at, just so we have some base knowledge of what's going on at the site. So there is some travel involved. It's maybe once or twice a month for me. I was actually just in Charlotte yesterday for a client presentation. So it just kind of depends. It's not too bad. But it definitely is necessary because you need to go out and figure out what's going on at the plant. And then you usually have preliminary reports. So once you start the design, the client wants to know that you're kind of going on the right track and you're not just, going off in the middle of nowhere with your design. So you usually have some preliminary reports, and then once they approve those, you can start the final design and finish out the project. And so from if you go to 0 to 100%, your preliminary report would be like a 30% level of design. So it's kind of basic, but you want to have general information in there just to make sure your idea will work. And all throughout the process, you usually have multiple client meetings just along the way to make sure everything's going smoothly, that you're meeting their needs, and that you're meeting their needs and expectations. And also, every once in a while, they may be like, hey, we like this, but we also want to add X, Y, and Z. And so you have to kind of balance that with, a lot of times they have a specific budget that they can't go over. So it's kind of balancing their needs and their wish list items. And then you have at some point you're going to have a final design. You're going to stamp those drawings with that stamp I was showing you. And then it's going to go out to what we call bid for construction. So just how we had to win the design, contractors have to win the construction side of the project. So they'll bid, they'll say, hey, it's going to cost $5 million for me to build this plant or this system. And usually it's the low bid wins on that. So specifically going into electrical design, the big thing, as I said, is power. So we're taking power from the utility company. We have, big panel boards. So you think of the panel board in your house with circuit breakers. Multiply that size by 10 and even larger, and that's the size of the equipment that is usually our main panel board for a plant. So we're sizing that type of equipment. We're sizing all the cables and the conduits that the cables are going in. We're specifying how the motors are going to start, because if you just give motor power, it's just going to run. So you need some way to some way to start and stop it. And then there's some starting methods that can control the speed, because motors are built usually to one speed. That's just the nature of motors. You give it power, it's going to spin at 1,800 RPMs. So sometimes the pumps, they need to vary the flow based on the demand for how much, what the demand is of the consumer. So we have to design around that a little bit. We also design generators. We specify the size of generators, I should say. So we would work with manufacturers to say, hey, we have a project. We're going to need a generator of this size, or we could tell them all the different motors and all the lights and all that, whatever that wattage adds up to, and then they will say okay, you need a 500 kW generator, and then we'll include that in design. There's also we have software that helps us do lighting design. We have to lay out all receptacles. A very important part of the code requirements is grounding of everything. For one, to help with short circuits. Another, to help with if there's lightning strikes. And also just to kind of have a reference voltage.
We have a question from online.
Oh, yeah.
What's the most interesting one of these projects that you've done this for? Does one stand out?
Yeah, so one of the, so I would think one of the biggest projects, I should say, is that when I was in Dallas, I worked on a project that the it was interesting just because the sheer size of everything. The pumps were 5,000 horsepower, which is insanely large, and they had 5 of them. And so I'm trying to think, the motor starter, the thing that's controlling the motor, was 40 feet long. And so our electrical room was about 100 feet by 100 feet, so the sheer size of this pump station was just enormous. And actually, we were having issues because everything was so large, is getting equipment that's rated large enough, like the ampacity, getting equipment that, because you can design something to be like, oh, it's going to be 10,000 amps, but you have to see if they actually make that equipment. So that's why you have to work with the manufacturers. You have to make sure they make certain things. So the issue with that was the actual motor starters. They were running up to the highest level that they actually provided at that voltage. So that one was pretty interesting, and unfortunately I didn't get to see it. We moved before it actually got built. I got to see the design through, but I've recently seen, I actually have a few pictures in here that I found that I had someone send to me. So I'll show some of those, and that's probably one of the more interesting ones, just because I haven't seen anything of that size. Usually our pumps are, even the largest ones are upwards of 500 horsepower. So we were talking a factor of 10 on that one. Yeah.
What is your main grounding tool? Or what do you use mainly for grounding?
So grounding, so there's kind of 2 different things. So for grounding, every piece of equipment that you send power to, you have to have a ground wire go. So you bring your power, like for instance to this light, you'll bring your power wires, but you also bring a grounding wire that connects to the metal fixture. And so say there's a short inside that fixture, that way it will create a short circuit path back to the circuit breaker, and it'll trip that circuit breaker. Basically, it's for protection against mainly personnel, but also equipment too. Once it's short, it probably needs to be replaced, but it helps it so it doesn't cascade up and you have a larger issue. So that's really, so we just have to make sure, and there's also, you can't see it, but there's probably a grounding ring around this building that also helps everything, all the grounding's kind of tied to 0, so you have like a reference point for your voltage. And it also it helps a little bit with lightning strikes. And so that's what I meant by grounding, but every project you need to, that's a code requirement. A lot of, for our oh yeah, go ahead.
Sorry, when you say code, are you referencing the NEC or you guys use different code?
Exactly,
I
the
mean,
NEC,
okay,
yeah.
so it is the NEC. Okay.
Yep.
Gotcha.
And I have a few more listed later on in the slides, but that's our main one.
Okay, I didn't know if you were talking like programming code for a second.
No. So, no, code book, yeah. So that's the National Electric Code is basically what we design around. And then other disciplines, whether you're structural, architectural, you'll have other building codes and things like that. But for electrical, that's the main one. And that's when they're building. So it's with design, and then when they're building the stuff, the electrical contractors have to follow that as well. So they're building, or we're designing around it, they're building around it. So even if there's something we miss in a design, and they say we miss something and they install something incorrectly, by code they will have to fix it. Whether who pays for that kind of gets thrown up, and you have to work that out. But things need to be, whether it's designed correctly, things need to be installed per the code as well. On the left, I kind of have the main items that I deal with mainly. Depending on the building, you can have fire alarm, security, telecom, access control, and then actually a lot of the buildings will have lightning protection, but that's it's not exactly a code requirement, it's more of a recommendation. But depending on the building, like I said, I worked for another firm for a year that did mainly commercial buildings, and so the right column, I would actually deal a lot more with the stuff on the right column. We would do a lot more fire alarm. Like for instance, this building, there's probably a very complex fire alarm system. I can see a few devices in here. But for us, a lot of these buildings are not really occupied, so we don't have to deal with some of those items. So it just kind of depends what industry you're in. And so right here, I show some of the software that we use. We heavily use computer-aided design, and the two big ones are AutoCAD and Revit. We're kind of switching from AutoCAD to Revit because it's a very powerful 3D software. You design, you put everything that has this 3D database, and you can give that to the client and walk them through the model, and so they can see everything in 3D, whereas years ago it was only just seeing these 2D plans. And on the right that's just an AutoCAD drawing. This is showing just a small pump station off a ground storage tank. So I'm just showing some of the stuff we have. Just some pumps. I show a little bit of lighting off to the right. Basically it's a lot in AutoCAD. It's all 2D. You just have a bunch of symbols, but really it's just kind of tying everything together and making something presentable that the contractor can look at, build, and price, and then build. And then the other ones, lighting software, you can do it by hand, but it'd be very tedious. So visual, AGI, those are some of the softwares. And then another item that I should have had listed on the previous slide is power system analysis. So we have to do short circuit studies, arc flash studies. Those are the two big ones. So you want to know, really it comes down to arc flash, because that could be something dangerous where literally the equipment will just blow up and could severely hurt someone. So we do these studies to kind of see how much, you really do it to see what is the ampacity that could, if there was a short circuit that could come through this system. And then the arc flash study kind of then generates what the energy is and basically tells you how far you should stand away from this equipment. If you're working on it while it's operating. If you shut it down, then you're safe. But so some of these are SKM, ETAP. Those are the main ones that we use. So yeah, if you're thinking about this, really thinking about AutoCAD and Revit, those would be some good ones to learn. Or if there's a class that's offered that has that uses some of those, that's something that we really look for when we're hiring. Is if you have really any of these, but I mean AutoCAD and Revit are the really big ones because they're kind of the backbone of our designs.
Do you see AutoCAD going away now that we have 3D modeling software?
For electrical, not 100% because of what I have on the board right now. So Revit's great when you're showing things in the building, so you can literally put it in a 3D light. The architects can have the 3D walls and everything. But for electrical, the other side of things is we have a lot of power flow diagrams, which is, we call them one-line diagrams. And this is much easier to do in AutoCAD than Revit. AutoCAD works much easier when you're just doing lines and shapes. Revit is really like putting in physical 3D objects into an overall model. So what I have here is this is kind of like the basis of our design, of electrical design. We show on top, it's usually our main panel board, or in this case, it's when you get to very large equipment, it's a switchgear. That's just what it's called. So from the top, you take in power from the utility, and then all these lines going below that main box that's the distribution for the entire plant. So you asked me previously what one of my other favorite projects. This is probably one of them too. This is in Tennessee, and this one was just really interesting because of the voltage. This is 23,000 volt system, and typically, like right now, all these lights, they could be 120 volt or 277 volt, depending on what they decide to do with this building. And usually that's the range we're looking at, anything from 120 to 480 volts. So this being at 23,000 volts was just a whole nother animal. So all through the system, we just have many transformers to bring down the voltage, other boards, and then ultimately what we do is we go a little bit further and we show all these essentially circles on the bottom are the individual motors. And so we show all the power, we show the circuit breakers feeding that, the starters, so we size all the wires going to it. And so these are kind of what our drawings look like, showing what the main breaker size is, which is way up here, the individual breaker sizes, and this is actually a motor starter. This is a different type of motor starter. This is a VFD, which actually helps change the speed of the motor, which I talked about a little bit earlier. So this is kind of like, this is like the main part of our design, is showing all the connections from the, basically from the utility down to the individual load. And this, I just kind of threw this in there. This is kind of, you know, because we have these 3D softwares, we can put something like this on the drawing as well, which shows, you know, I'm showing the transformers. We have the generators up a little bit north. So this had 2 transformers from the utility, 2 generators. And then we have, you can see this whole lineup of equipment a little bit. That's, a lot of those is like one real big piece of equipment. So this is just kind of the cool stuff we can do with the 3D modeling. And this is the stuff the clients really like to see as well. So I told you I wanted to show you some photos. So actually from that, so this picture right here, this was also in Galveston. This plant got knocked out by Hurricane Ike, I think in like 2005. So we designed a new system, and what was interesting about this one is everything, including conduit and wire, had to be elevated above the floodplain. So you could see every building was on piers. That's why the transformers are on this like large platform. And so it was a little weird because usually when your wires are going from one building to another, you go underground. A lot of times, for us, we go underground. Utility companies will do utility poles going along the streets, but we usually do everything in the ground. But even for this, we had to keep everything above like a 10-foot elevation off the ground, just because we were trying to meet a certain floodplain level. And as you can see, this is the plant right here. You can see how close it is to the Gulf of Mexico. It's literally almost sitting right there. So, so everything was elevated, and this is the final construction. So that's a wastewater treatment plant. And then here, this is a 4,000 amp switchboard. It's powering a bunch of like 300 horsepower, 400 horsepower blowers, which is just other than pumps. Sometimes you have blowers, which just helps aerate the water. These are some high service pumps. So these are the type of pumps that will distribute water to you guys, to all residential, all commercial buildings. And then here's just an example of the actual what the equipment looks like for the motor starters. These are the starters that can change the speed of a motor. Then I just had a few more. I mentioned the one with the 5,000 horsepower pumps. So that's that right there. It's hard to tell the scale, but if you were standing next to it, it would probably be twice as tall as you. Yeah.
You mentioned the starters, and you also mentioned the variable frequency drives. Are they both the same, or are they different parts?
So a starter.
Repeat that question.
Yeah. So yes, is a motor starter and a variable frequency drive, are they the same, or are they different pieces of equipment? Is that essentially, yeah. So a motor starter is really a generic term. So a variable frequency drive is a motor starter, but there's many different types of motor starters. So the main 2 are just your standard, we call it across the line, because all it does is it closes a contact and you just get power, that's it. And the motor will spin to the speed that it was built to go. Variable frequency drives has a lot of parts and pieces to it, a lot of transistors switching on and off to change the speed. It basically varies, it says variable frequency, but it really varies the voltage and the frequency together to change the waveform of power going to the motor, and it'll change the speed. And so this is just this is that pump station. So these pumps, and the next room over is the electrical room. So this is just the equipment still in construction. So we have like 2,000 amp. This is basically a bunch of motor starters side by side by side by side by side. And then here is the switch gear this switch gear is feeding that motor control center. And then this right here is actually, so one part of treating is actually, once you've kind of separated water from other stuff. You want to get the water, you want to extract as much water as possible. And so these are centrifuges, which just spin really fast to separate the water, separate the solids from the water even further. Oops. Okay, and so we were talking about the codes, the different codes. So the National Fire Protection Association, NFPA, they have, you can see the numbers are going from 70 to 820. So they have many, many codes. And the whole point of them is safety, prevent fires, prevent harm. And our main one, as we talked about, is NFPA 70, which is the National Electric Code, which I have there in red. That's our main one that we design around. That tells us how we size cables, circuit breakers, how close equipment can be together. The ground, it tells us how to do the grounding system. So we really look at that. I mean, I'm looking at that thing daily. The reason why, I'm sorry, and so some of the other ones that we use, 70E talks more about that arc flash, which in the upper right-hand picture is what you're seeing. That's an arc flash. So that equipment, something happened in there where it's causing to explode. So 70E talks a little bit about arc flash requirements and what you can do to help protect yourself from that, or the personnel. NFPA 101 is life safety, 110 is emergency generators, 497 is chemical systems, 780 is lightning protection, and 820 is actually very specific to wastewater treatment plants, because the wastewater treatment plants will release combustible gases like hydrogen sulfide, methane, and so we have certain codes. They actually make panels that are called explosion-proof panels, which is essentially a giant box bolted together with about however big the box is, but it's just a bolt every inch all the way around it. So it makes it so it doesn't prevent an explosion, but it keeps it contained in the panel. So all these codes are really to prevent what's happening here, and then this is actually at a wastewater treatment plant, and I found it online from California. I'm not sure exactly what happened. I think it was actually a truck that had some residual stuff that they loaded up into the truck from kind of like the byproducts of the wastewater filtering, left in the truck, and somehow it ignited. And then the upper right is, this can happen if, so basically I said you want to see how much short circuit current you can have. If the breaker doesn't, it can happen a few ways. Maybe sometimes you see where maintenance personnel might leave a tool. If they're working on it, they might leave a tool inside, and that tool finally falls after they've left and they've energized everything again. If that tool falls, it's going to hit two copper bars inside the equipment, and then you'll get an explosion like that. Or if you get a circuit breaker that's not operating quite correctly, something like that could happen.
Heather Hodge wants to know about OSHA guidelines. OSHA, excuse me. OSHA.
So, trying to think, a lot of those guidelines are we follow them by default by just following these other codes.
Training though, as an engineer, are they?
So I actually, that one company I went to for a year, I had to go to a 10-hour OSHA training class. But the company that I work for now, they didn't require it. It kind of depends. I think OSHA, a lot more issues come for them during construction they have to follow. And some of the things that we have to do is we'll follow them just by the nature of the other codes we have to follow. And so wrapping up, really, so some of the advice I have is really to, things we look at is try and keep that GPA up as high as best you can. Coming in as a recent graduate, you're most likely not going to have a lot of experience unless you did have a lot of internship experience. So some of the things we look at is just, your overall GPA, how well did you do in class, kind of gives us a look into like what type of, like, are you a hard worker, things like that. And if you have the opportunity to get into a co-op or an internship, definitely take it. Especially, like I said, if you can, with a consulting firm, if you can learn AutoCAD or Revit or one of those computer-aided design programs, that's something that'll really jump out at us. As a recent grad, that'll really jump out at us on your resume, so make sure you put that on there if you learn it. Definitely start your resume and practice interviewing. And try and tailor your resume to the job, because I know that there's only so much sometimes that you can put on a resume. So maybe try and think of what is this company looking for. Like for instance, our company, if you have Revit or AutoCAD, try and put that on there. But if you're looking at another company that they're not a consulting firm, maybe they're the manufacturer or something, they might not need that as much. So kind of tailor it to the job you're looking for. If you can take the FE while you're in school, go ahead and do it. It'll probably save you some studying, some additional studying after school. The big one, go to job fairs. That's how I found my first job. So go to job fairs. They do work. So if you can, go to some job fairs. And just CDM Smith, we do hire about 100. This is actually old, so I think it's probably gone up a little bit, over 100 new grads every year in different offices. And then we also do have some internship and co-op opportunities. So if you're interested, look at our website. All the new grad or recent grad stuff will be on there. And that's all I have. So any additional questions? Thank you.
We have a token of our appreciation for you.
Oh, thank you.
Very much. So our STEM speaker series is the 4th or last Wednesday of the month at 2 o'clock. So next month is Halloween, and we have Dr. Tyler Allen, who is a cancer biologist and is on the Forbes top 30 under 30 for the nation. So I hope to see you next month. Thank you very much.